also extend my welcome for the first lecture of the 2021 New Vistas in Astronomy series. Today, we are very honored to have Dr. Avi Loeb from the Center for Astrophysics in Harvard and Smithsonian. Dr. Loeb received his PhD in plasma physics from Hebrew University of Jerusalem at the age of 24. He is the Frank Baird Junior Professor of Science at Harvard University, the chair of Harvard's Department of Astronomy, the founding director of Harvard's Black Hole Initiative, and director of the Institute for the Theory of Computation within the Harvard Smithsonian Center for Astrophysics. He also chairs the advisory committee for the Breakthrough Starshot initiative, serves as the science theory director for all initiatives of the Breakthrough Prize Foundation, as well as chair of the board on physics and astronomy for the National Academies. He's also a member of the President's Council of Advisors on Science and Technology. Dr. Loeb is an elected fellow of the American Academy of Arts and Sciences and American Physical Society and the International Academy of Astronomics. In 2012, Time selected Dr. Loeb as one of the 25 most influential people in space. Dr. Loeb is the author of 8 books and over 750 scientific papers on a wide range of topics, including black holes, the first stars, the search for extraterrestrial life, and the future of the universe. His latest book, Extraterrestrial, The First Sign of Intelligent Life Beyond Earth, was published January 26, 2021, and was an instant bestseller on Amazon. And this week, it made number 6 on the New York Times nonfiction bestseller list for print and ebook. So today, Dr. Loeb will be speaking to us on extraterrestrial life. Are we the sharpest cookies in the jar? So welcome, Dr. Loeb, and it's all yours.
Thank you so much. It's a great pleasure to join you virtually. I wish we could all meet in person, but that's what we can have at this point. So let me share my screen and open my presentation. And so today I will discuss some of the main topics in my new book that just appeared about a week ago. And if I had to summarize it with one sentence, I would say, when you are not ready to find exceptional things, you will never discover them. And this was the title of a Scientific American article that I wrote a few months ago. And you can see the cover of my book, and also on the left, what you see is a photograph of a photograph that was taken by Herlinde Quilbel. She's a very famous German photographer who asked me to write the single most important question that I can think of in the context of modern science. And I wrote down, are we alone? This appeared in an exhibit in Berlin just a few months ago. So let me start with explaining my fundamental perspective, which is modesty. And that's the biggest message that I got from the sky as a professional astronomer over the past few decades. When you see the universe, there is no escape from the realization that we must be modest. I just cannot understand how people can be arrogant on Earth. And I'll get into that in a few minutes. So let me read an excerpt from my book that summarizes my thinking, and it's related to my parents who passed away over the past few years. My father, David, was laid to rest in the same red soil in which he planted trees all of his life, in the vicinity of those plantations that he watered routinely, near the house that he built with his rugged hands and that I grew up in, surrounded by the people he loved and who loved him in return, under the blue skies that I study as an astronomer. My mother, Sarah, who put me on the road of thinking as a philosopher, with whom I spoke daily throughout my adulthood, and who especially gifted me with a life of the mind, was buried beside him 2 years later. In astronomy, we realize that matter takes new forms over time. The matter we are made of was produced in the hearts of massive stars that exploded. It assembled to make the earth that nourishes plants that feed our bodies. What are we then, if not just fleeting shapes taken by a few specks of material for a brief moment in cosmic history on the surface of one planet out of so many? We are insignificant, not just because the cosmos is so vast, but also because we ourselves are so tiny. Each of us is merely a transient structure that comes and goes, recorded in the minds of other transient structures. And that is all. So what I fail to understand is how come some people adopt arrogant views, think highly of themselves, and you find those portraits of alpha males standing up with a sword and being very proud of themselves, like this one. I found it on Google Images, very easy to find. We know that there are more habitable Earths in the observable volume of the universe than there are grains of sand on all beaches on Earth. Just think about it. About half of all the sun-like stars host an Earth-sized planet roughly at the same separation. And this is a scientific result that was published just a few months ago based on the Kepler satellite data. So not only that we are not at the center of the universe, as the ancient Greek philosopher Aristotle suggested, but even the circumstances in our backyard, the Earth-Sun system, are very common. We find it everywhere. And of course, people believed Aristotle for 1,000 years because it flatters our ego to assume that we are at the center of the universe. But the point is that if you check the facts, we are not. We are not central for anything. And therefore, I would like to advocate a sense of cosmic modesty. By the way, it would help us also as human beings to adopt this sense of modesty, because the biggest evils in human history were caused by arrogance, by people pretending to feel superior relative to other people. Racism is a good example. The color of a skin, how can that make any difference whatsoever to who a person is? And if you view the universe at large, all of these differences between us become minuscule, completely insignificant. As Oscar Wilde said, we are all in the gutters, but some of us are looking at the stars. So speaking about the stars, these emperors and kings, like the one I showed in the portrait before, that conquered a piece of land and therefore were very proud of themselves, resemble an ant that hugs a single grain of sand on the landscape of a huge beach. It's not very impressive. It's quite ridiculous if you think about it. But I can understand it because my two daughters, when they were young, they tended to think that the world centers on them and that they have special qualities that nobody else shares. But then they went to the kindergarten and they met other kids and they got a better perspective. Those kids, some of them had better qualities. And so our civilization will mature only by leaving our home and meeting others out there. We are probably not the smartest kid on the block or the sharpest cookies in the jar, where by the jar I mean the Milky Way galaxy. And that is based on the news that we see every day. Humans do not behave in a very intelligent fashion. I mean, we fight each other, we waste a lot of resources on destructive measures. Doesn't make much sense. We should be cooperating towards a better future, but we are not. And so my view is that aliens probably don't find us particularly interesting because we haven't demonstrated intelligence as of yet. So one reason I look for intelligence in the sky is because I don't find it on Earth very often. Speaking about Earth, I mean, we know that it's our home right now, but only for a while. There are risks from internal catastrophes like climate change, non-conventional wars, pandemics, political or technological catastrophes, self-inflicted wounds, so to speak. But there are also risks from impact of asteroids. We know that the dinosaurs were killed by a huge rock that impacted the Earth 66 million years ago. The view must have been beautiful to look up and see this rock getting bigger and bigger, but the fun stopped when it hit the ground. And although the dinosaurs had much larger bodies than we do, you might think, oh, they could have survived better. But in fact, it's the human brain that allows us to survive far better than the dinosaurs. Astronomers can use telescopes to figure out that an object is approaching us and then alert everyone to deflect that object. So we have a better chance of survival from asteroid impacts. But there are other dangers, supernovae, the sun, in fact, within a billion years or so, will boil off all the oceans on Earth due to a greenhouse effect. And so we have to move out. We will have to move out at some point. Speaking about moving out, let me describe my journey from childhood to Harvard, the Harvard Smithsonian Center for Astrophysics. So I was born 59 years ago, minus a couple of weeks, on a farm in Israel. I used to collect eggs every afternoon, as you can see in the second image on the left. We had chickens, and I used to drive the tractor, which you can see in the middle image. Here I'm sitting next to my sister, but in general, I used to drive the tractor on weekends and read philosophy books on the hills of the village. Philosophy appealed to me because it addresses the most fundamental questions that we can ask, although we don't have good answers for most of them. And then circumstances led me eventually to arrive to Harvard and get tenured there in the astronomy department. And I've been the chair of the astronomy department for the past 9 years, longest serving chair in the history of the department. But I always viewed my involvement in astrophysics as a compromise because I enjoyed doing philosophy at a young age, until I realized that, in fact, astrophysics addresses the most fundamental questions using the scientific tools that we have. And one of these fundamental questions is, are we alone, or are we the sharpest cookie in the jar? On the right side, you can see my family, my wife and 2 daughters. And in 2015, a black limousine parked in front of the Center for Astrophysics, and an entrepreneur from Silicon Valley, Yuri Milner, stepped out of it and came to my office. And he asked me whether I'm willing to lead an initiative to visit the nearest star, Proxima Centauri, within our lifetime. And since Yuri and I are the same age, what it meant is within 20 years. But the nearest star, Proxima Centauri, is 4 light years away. That means that it takes light 4 years to get there. So that if you want to get there within 20 years, you need a spacecraft that travels at 1/5 of the speed of light. And that's not easy. So I had my students and postdocs think about potential technologies that can achieve this task. And after 6 months, I recommended the only one that looked feasible. And we announced it on April 2016 in the company of Stephen Hawking in New York City. It was funny because on the same day that we announced it, April 12th, my wife brought our car for oil change, and the mechanic asked her, "Where is your husband?" And she said, "Well, he's announcing the Starshot project in New York City." And then the mechanic said, "Wow, that's amazing. I've been following this project all day, and it's really extremely exciting. I'm really interested in all the details." And to me, that illustrated the fact that, since the 60s, since the Apollo program, we haven't had an exciting space endeavor, something that will bring the public's interest to space and inspire a lot of people. And this was one of these projects that does inspire people. So here is a picture of the solar system. At roughly, you see the sun on the left, the Earth, and then at roughly 10 times the Earth-Sun separation, we find the Saturn. And then at 100 times the Earth-Sun separation, the solar wind, the wind that comes from the sun, is stopped by the interstellar medium, the gas that fills the void between stars. And there is the so-called heliopause there. But the solar system extends far beyond that. In fact, it goes all the way to 100,000 times the Earth-Sun separation. And the outer part of the solar system is called the Oort cloud. It contains rocks that can be thought of as just Lego building blocks left over from the formation of the solar system. So the planets were made out of the debris left behind from making the sun. And then the building blocks of the planets are these rocks, some of which were scattered and ended up in a sphere around the sun called the Oort cloud. And it turns out this sphere extends roughly halfway to the nearest star. And what that means is that if the nearest star has an Oort cloud, then the Oort clouds are touching each other. You can think of them as billiard balls that are densely packed. So as stars move near each other, the Oort clouds are grazing. Space is almost full of Oort cloud objects, and it's easy to rip apart those loosely bound rocks and make them a population that is interstellar. So the most straightforward origin or source of interstellar objects is the Oort clouds around stars. And those include rocks that are covered with ice. And when such rocks get close to the sun, they become comets because the ice is evaporated and you end up with a trail of gas behind the object. And these are called long period comets. They have a long period if they come all the way from the Oort cloud to the sun. And this is an artist's illustration of Proxima Centauri, the nearest star, which happens to have a planet in the habitable zone at a distance where liquid water may exist on its surface. But since this star is 12% of the mass of the sun, it's a dwarf star. It also has half the surface temperature of the star, so about 3,000 degrees Kelvin. The habitable zone is 20 times closer than the Earth-Sun separation. And at that distance, the planet is tidally locked, meaning that it faces the star always with the same side as it orbits around it. So the orbital time is 11 days. So if there are any living creatures there, they celebrate their birthday every 11 days. There must be a lot of parties over there. But there is a permanent day side and a permanent night side. And they are separated by a permanent sunset strip. And my daughters say that the real estate value on that strip will be the highest because you can see the sunset forever. And if we ever move there, they want to live on that strip. But if you imagine, for example, creatures that are born on the day side, the permanent day side, they should have infrared eyes because most of the light emitted by the star is in the infrared, since it's much cooler than the sun. Actually, most of the stars in the Milky Way galaxy are dwarf stars like Proxima Centauri, and they would live for up to 1,000 times or thousands of times the lifetime of the sun. Maybe that explains why interstellar tourist agencies never advertise the Earth as a desired destination for vacations, because if most stars are like Proxima and they emit mostly infrared radiation, then most creatures have infrared eyes and they are used to dark red grass on their planet. And they would never find it appealing to come to a vacation site that has green grass and visible light. That would hurt their eyes. So they would never come to visit us. The only way for us to get their attention would be to go there and offer them a water-based drink and try to entice them to visit us. And so speaking about going there, that's the Starshot project, to get to the nearest star. And the only technology that could make it feasible is called the light sail technology, meaning that it involves a sail, just like the sail on a boat, which is pushed by wind, except here it's being pushed by light. So when light bounces off a surface, if the surface is thin enough, the light can push it to high speeds. So in particular, if you have a beam of laser that is very powerful, laser light of 100 gigawatt or so, shining on a sail that has roughly the dimensions of a person, a few meters in size, and a weight of about a gram or a few grams, then within a few minutes, that sail will reach 1/5 of the speed of light across a distance that is 5 times the distance to the moon. And in principle, you can put on that sail some electronics that includes a camera, communication device, a navigation device, all weighing less than a gram. That kind of electronics already exists in cell phones. And the light sail concept was already demonstrated, not with a laser, but with sunlight. And you can see it on the right side. Light Sail 2 was deployed by the Planetary Society in 2019. So here is the concept in a video. There is a whole collection of low power lasers that combine their beams into a single powerful laser beam that is focused on a sail that is released above the Earth's atmosphere so that the friction will not slow it down. And then the laser beam reaches that sail. The sail was released from a mother spacecraft. And every day or so, one can release a new sail. The sail doesn't cost much, maybe the cost of a cell phone. So in principle, you can send many sails over time. And then you launch it into its trip. It takes only a few minutes to launch it, but then the trip itself takes 20 years. And it's rather boring. That's why humans probably would not want to be engaged in such a trip. You want to send electronics. And after 20 years, the sail or the spacecraft will get close to the planet, take a photograph of the planet that can inform us whether there is life on it, and then send us back the photograph. And it will take another 4 years for that signal to reach us. It will be very faint, this signal, because the distance is vast. The 4 light years is a huge distance, and the beam will spread and occupy a scale that is bigger than the Earth-Sun separation. But with a proper telescope, we can detect the signal and see that photograph. And of course, the fundamental question that we want to answer is, are we the smartest kid on the block? If you open recipe books, you realize that you can start from the same ingredients and get very different cakes out of them, depending on how you mix them, how much heat you apply in the process of baking. And therefore, even though there are so many planets that resemble the Earth, billions of them in the Milky Way galaxy alone, Earth may have not baked the best cake that we can imagine out of the random processes that started from the initial soup of chemicals and ended up in life as we know it. The chance that we are the smartest kid on the block, I would say, is rather small. And we see evidence for that in the way that we behave. Of course, you know, if I were to ask my daughters whether they want to go to the kindergarten or stay at home, they would prefer to stay at home because that flatters their ego. They can still think that they have superior qualities. And, you know, that's what my colleagues also say. They say, you need to show me extraordinary evidence that alien civilizations exist. So I need to bring them an alien that will shake their hand before they actually are willing to discuss this possibility, which is, you know, it's unfortunate because if you're not looking for exceptional things, you will never find them. So if the search is not funded, if young people are discouraged from being engaged in such a search, then the situation is similar to stepping on the grass and then claiming, look, the grass doesn't grow. Obviously, if you do not nurture it, it will never grow. So my recommendation, on the other hand, is that we should have no prejudice, that in fact, it's very likely that we are not alone and that life as we know it here is very common, because if you arrange for similar circumstances, you might as well get the same outcome. And that would be the most conservative and commonsensical thing to say. So the scientific community should actually be using this assumption as the mainstream view and then conducting the search. But instead, this subject is in the periphery. It's being pushed aside and is not discussed much. There is not much search for technological signatures. Of course, searching for primitive life is considered mainstream because it poses no threat to our ego, and people are willing to engage in that. Now, it's not a matter of avoiding risks in research, because if you look at the search for the dark matter, most of the matter in the universe, for example, is not known. And we have been searching. There were ideas for weakly interacting massive particles, for axions. These were proposals made, and hundreds of millions of dollars were invested in searching for such particles without success. And after several decades of not finding the dark matter, you know, people still claim it should be part of the mainstream and we should continue to search. We are searching in the dark for the dark matter. We don't know what kind of particles it represents. So I would not regard the search for technological signatures as more speculative. In fact, it's less speculative than the search for dark matter, because we know that we exist and we know that the conditions on Earth are replicated in billions of other systems within the Milky Way galaxy alone. And then you have trillions of galaxies in the observable volume of the universe. So it's really strange to me to find this situation. The astronomy community should be exactly in the opposite position to where it is. Instead of ridiculing such a discussion, they should be embracing it. I really do not understand my colleagues on this subject. And the public has its heart in the right place. The public does have common sense. The way I view it is that a lot of academic activity these days is done in order to avoid making mistakes, amplify your image so that you can get honors and awards, and not taking any risks, not going in paths that were not explored in the past. But we know, for example, that Albert Einstein made 3 major mistakes in the last decade of his career. He argued that black holes don't exist, gravitational waves don't exist, And he argued that quantum mechanics doesn't have spooky action at a distance. And all three were proven wrong by experiments later on. But that's part of the process. Science is a learning experience, and we should allow ourselves to make mistakes, to take risks. And so why wouldn't we search for technological signatures? You know, we might not find them immediately, but just like the search for dark matter. And the best place to start the search is in our backyard. So the situation is similar to going to your yard and looking for objects that arrived there from the street. It took these objects millions of years to travel through interstellar space before they arrived at our doorstep, inside the solar system. So they saved the trip. Instead of us going there, they arrived here, and we can examine them and learn about the environments that are very far away. And the first object that was discovered from outside the solar system was found by a telescope named Pan-STARRS on the summit of Haleakala in Maui, Hawaii, on October 19th, 2017. This is the image that shows this object. It was given the name Oumuamua, which means a scout in the Hawaiian language. And what you see are streaks of dots which represent background stars. So if you focus your attention on the object, the background stars are moving relative to it because the object is moving very fast. And so they appear as a sequence of dots, each representing a snapshot. And this is where the object came from in the sky. It started on the top right corner of this diagram. And you can see in purple there, anyone that is an amateur astronomer would recognize the solar apex. What that means is this is the direction that the sun is moving towards in the so-called local standard of rest. The local standard of rest is the frame of reference that you get to after you average over the random motions of all the stars in the vicinity of the sun. So each star has some velocity that is different from the other stars, but you take the average of those velocities, you end up in the local standard of rest. And the sun is moving relative to that frame in some direction. This is the solar apex. Now it turns out that Oumuamua was at rest in the local standard of rest, sort of like a buoy on the surface of an ocean, and then the solar system acted as a giant ship that bumped into it. And that is very unusual because only 1 in 500 stars is so much at rest in the local standard of rest as Oumuamua was. Of course, after the sun bumped into it, it was kicked by the gravitational force of the sun. And this is the trajectory that it went through. The relative velocity of us and Oumuamua was simply the velocity of the sun relative to the local standard of rest. Very unusual situation. We don't find objects sitting at rest in the local standard of rest. But there was another peculiar feature of Oumuamua. Its brightness changed by a factor of 10 or more. And the brightness stems from reflected sunlight. And the amount of reflected sunlight is proportional to the area of the object on the sky. So as the object tumbles or spins over an 8-hour period, the area that it occupies on the sky changed by at least a factor of 10. And what that means is that projected on the sky, it was at least 10 times longer than it was wide. So think about a razor-thin piece of paper tumbling in the wind. Even though it's razor-thin, you know, the chance of us seeing it exactly edge-on is really small. So a factor of 10 in the area that we see as it is tumbling is a large factor. It means the object has an extreme geometry. And the best fit to the light curve at the 90% confidence level was that of a pancake shape. not cigar-shaped. The cigar shape is what you see on the sky. That's the projection. But the intrinsic shape of the object was pancake shape. Very unusual for a rock. And this is the trajectory with the dates on it. So in July, it was approaching us, July 2017. And then when it was detected, October 19th, it was receding away from us. Sort of like finding a guest on his way out from the front door into the dark street. So it's a little late, but you can still get some impressions of that guest. And as it turns out, I was visiting with my family the island of Maui in Hawaii, and I was asked to give a seminar, a colloquium at the observatory, and I visited Mount Haleakala in July 2017. If we were to know about Oumuamua back then, we would know that it's approaching us, and perhaps we could have sent a camera that would get close to it and take a close-up photo. But we didn't know about it in July, unfortunately, only in October. It's a lesson for the future. The next object that we see of this class, we should try and find it early in its trajectory. So it turns out this object was weird on several counts. I mentioned a few of them, but actually what I didn't mention is the mere detection of this object was surprising, because a decade earlier, I wrote the first paper forecasting how many interstellar objects we expect. That was a paper written with Amaya Morrow-Martin and Ed Turner. And we predicted that pan-stars will find nothing. We were off by orders of magnitude from the necessary population of interstellar objects that would account for the detection of Oumuamua. So that was a surprise that an object appeared, because just based on the analogy with the solar system, what we know about rocks in the solar system and how many of them can be ejected over the lifetime of the solar system, and assuming that other planetary systems are just like the solar system, we would expect nothing for pan-stars. Only for the next observatory called the Vera Rubin Observatory in Chile that will become operational in 3 years and will have greater sensitivity. Only we infer that only that telescope will be able to see something. So we were wrong, and there are many more interstellar objects than we expected. The other peculiar fact about Oumuamua was that it originated from the local standard of rest. And as I said, the chance for that is 1 in 500. Because if most of the interstellar objects reside in the Oort cloud of other stars, because that's the region that is most loosely bound and can be easily ripped apart when another star passes by, then those objects that are ripped apart from the parent star will be very loosely bound, and therefore they will inherit the original velocity of their host star. But only 1 in 500 of the host stars has such a small velocity relative to the local standard of rest as Oumuamua showed. So that's surprising. And then it had an extreme geometry based on the variation of the brightness by a factor of 10. And in fact, we tried to extend the analysis beyond the 11 days during which it was monitored continuously into a few extra days when it was monitored later on. So with my student, we showed that the variation, so the long axis of the object on the sky relative to the short axis needs to be bigger by a factor of 30, not even 10. So it's even more extreme than that. And the best fit to the light curve is a pancake-shaped object. There was no heat detected from it. Based on its orbit, we can infer the surface temperature. The temperature of any object depends on its distance from the sun. So we know the temperature on the surface of that object, but the fact that the Spitzer Space Telescope didn't see any heat coming from it, any infrared radiation, implied that it must be smaller than some size, because otherwise we would see some emission from it, infrared emission. And that size was about 200 meters, a few hundred feet, the size of a football field. Must be smaller than that. If it were 20 meters in size, it needed to reflect all the sunlight on it, falling on it, for us to see the flux of reflected sunlight that we saw. So its reflectivity, reflectance, is on the high end of the objects that we see in the sky. It's a bit shiny. And the most peculiar fact about it is that it deviated from an orbit shaped just by the sun's gravity. There was an extra push away from the sun, but there was no cometary tail. We couldn't see any gas around it. The Spitzer Space Telescope looked very deeply around this object and couldn't trace any carbon-based molecules or dust to a very significant limit. So definitely not a comet. And without outgassing, what gives it this extra push? In fact, to get this extra push from cometary activity, from outgassing, you need about 10% of the mass of the object to be evaporated. That's a lot of mass. We would see such a cometary tail easily, but there was nothing. So it's not the rocket effect from outgassing that pushed this object. If not that, what else? So that's what brought me to the possibility that maybe it's the sunlight reflecting off its surface. And for that, the object needs to be thin, sort of like a sail, a light sail. And so we proposed that in a paper that we wrote with my student, with my postdoc, Shmuel Bialy. Now, since we wrote that paper, and obviously there was a lot of attention, we didn't really mean to attract so much attention. There was no press release on this paper. But in the subsequent years, there were mainstream astronomers that tried to explain the very weird properties of Oumuamua as originating from a natural source. I should say the scientific community, the astronomy community, divides into three parts. There are people that call themselves scientists. They write blogs, they write popular science books. Some of them are very famous, they're well known to the public, but they haven't written a single scientific paper over the past decade. You can easily trace that because there is an archive for all scientific papers. And these people never wrote even a single scientific paper over the past decade. I don't pay attention to what they say. They are not practicing scientists. They just pay attention mostly to the number of likes they get on Twitter. That is not of interest to me. Just like basketball coaches, we should keep our eyes on the ball, not on the audience. I don't care how many likes I have on Twitter. If someone were to show me through scientific reasoning evidence that what I consider to be artificial is actually natural, I would accept that. That's the scientific process. So the second part of the scientific community are people that are not involved in the details. They don't know much about rocks. They don't care much about the evidence, the peculiar properties. They just say, it's probably a rock. Forget about it. Business as usual. And then there is the small group of mainstream scientists that are trying to explain the observed facts from a natural origin. So what were the proposals that they brought up to the table? One was a collection of dust particles, a dust bunny of the type that you find at home, except this one is the size of a football field spinning around every 8 hours. And such an object needs to be 100 times less dense than air. So think about steam coming off a boiling pot and imagine something that is on average 100 times less dense than that, being the object Oumuamua, reflecting sunlight, and as a result being pushed because it's so lightweight, it's so porous. I have a hard time imagining that something that is 100 times less dense than air, the size of a football field, spinning around every 8 hours and traveling for millions of years through interstellar space, would survive. It's very loosely bound. Another proposal was maybe Oumuamua is a fragment from the tidal disruption of a bigger object that passed very close to a star. But what you get from such a disruption is very often elongated objects, objects that look like a cigar, not objects that look like a pancake. And also the chance of passing close to a star is very small. Most of the objects are not passing close to a star. And if we see the first object, it should not be, a typical object should not be the one that represents rare circumstances. And then there was the suggestion that maybe it's a hydrogen iceberg, an object made of pure hydrogen. And the advantage of that is that if it has a cometary tail, if it gets evaporated by sunlight, we wouldn't be able to see the hydrogen. And that would explain why we don't see a cometary tail. I should say that we have never seen a hydrogen iceberg in space. And we don't know if they exist. And in fact, I wrote a paper with Tim Huang that demonstrated that such icebergs of the size of Oumuamua would get evaporated very quickly by absorbing starlight along their journey. So they wouldn't survive the journey through interstellar space. And the authors of this proposal agreed. They didn't have anything to say about our calculation. So in all cases, you can tell that mainstream astronomers that try to explain the properties of Oumuamua from a natural origin had to invoke something that we have never seen before. And I say, if it's something that we have never seen before, why not put on the table the possibility that it's artificial? Why is that unacceptable? If at any event it's something that we have never seen before. And by the way, if we collect more evidence, I'm very much in favor of collecting evidence, we will learn something new, irrespective of whether it's natural or artificial. So why argue, oh, it must be a rock, therefore let's not even discuss it? Why not get motivated to get as much data as possible about the next weird object that comes along, and including the possibility of an artificial origin on the table? Why is that so problematic for most of the astronomy community? I don't understand that. Frankly, I'm speaking from my heart. You know, I was born on a farm, and I still regard myself as a simple-minded boy, you know, from that background. I just, you know, apply common sense, and I sometimes do not understand the reasoning behind the view of the mainstream. This is a citation, a quote from one of the first reviews of my book on Goodreads. I didn't really understand some of the words here, but my daughters explained it to me. So it's possible that Oumuamua is just a plastic bottle on a beach. Most of the time we see rocks that are naturally produced as we walk on the beach, but every now and then we see a plastic bottle. And it may be dysfunctional. It may not, you may not be able to use it for anything. And that should be true of, you know, Voyager 1, Voyager 2, New Horizons that we launched and will exit the solar system. In 1 billion years, there will be just junk, space trash. Most of the objects that are thrown into interstellar space will not be functional after billions of years, but we still could find them. So if we sit on a beach and we find a plastic bottle next to our feet, then we know that there is a civilization out there, and the chance of us seeing it is just dependent on the number of plastic bottles per unit area on the surface of the ocean, right? So if you wait long enough, you will find something. And it turns out that just a few months ago, there was another object that showed a push away from the sun as a result of reflecting sunlight, but no cometary tail. This object was given the name 2020 SO by the Minor Planet Center at the Center for Astrophysics. And here you see the orbit of this object relative to the Earth, not relative to the sun. So the object was actually in a very similar orbit to that of the Earth around the sun. And then the people that discovered it, when they extrapolated back in time, they realized, oh yeah, it's actually a rocket booster that was launched into space in a mission called Lunar Lander Surveyor 2 in 1966. So we kicked into space a structure that was hollow and had very thin walls. And because of that, the reflection of sunlight was effective in changing its orbit. And that demonstrates that we could tell the difference between a rock and an artificial object, in this case, produced by us. With respect to Oumuamua, the question is, who produced it? We don't have enough evidence. It would have been nice to get a photograph. Now, there was a second interstellar object discovered in 2019, and that's called Borisov, after the Gennady Borisov, the amateur astronomer from Russia that discovered it. This one looked just like a comet, like a regular comet, a natural object. And so people came to me and said, well, doesn't that convince you that Oumuamua was also natural? To which I replied, if you find a plastic bottle on the beach and after that you see a lot of rocks, does that change the nature of the plastic bottle? Or another way to say it, when I met my wife, I thought that she's special and unique. I met a lot of people after that, and I still think the same about my wife. Borisov has nothing to do with Oumuamua. You can have rocks and plastic bottles reside in interstellar space. So the fundamental question is, does Oumuamua did it originate from a natural or an artificial source? And of course, getting a photograph would clarify this matter. So I'm not fighting a popularity contest on Twitter on this issue. I just want a photograph. And our technology, that we have was developed over the past century. So if you look at cosmic history, this is the timeline starting from the left, the Big Bang, and then getting to the present time on the right. Our technologies were developed over the very last bit of time that is roughly 1 part in 100 million of the age of the universe since the Big Bang. Very recently. And by the way, the sun itself formed relatively late. It's a late bloomer. Most of the stars formed before the sun, billions of years before the sun. So if they ended up making technological civilizations like ours, these were billions of years earlier than us. And they deposited trash in interstellar space, and we can search for it. It's in the past, over the past 70 years or so, we've been searching for radio signals. That makes little sense to me, because it's just like trying to call someone on the phone, right? So in order to have a conversation, you need the counterpart to be alive in order to have a phone conversation. We cannot have a phone conversation with the Mayan culture because they're not around anymore. But we do know that they existed. How do we know? We have an archaeological dig where we find relics left from the Mayan culture. So if you are waiting for a letter in the mail, instead of trying to make a phone call, and you know that USPS is very slow, it's possible you will get the letter long after the person who sent it is not around anymore. And so by looking for physical objects rather than a radio signal, you are summing over the entire history of the Milky Way, of civilizations in the Milky Way, if they left relics in space. It's sort of like space archaeology. And around every star, there is a habitable region, a region where life may exist, which depends on the temperature of the star. And for planets in that region, one can look for technological signatures. So in addition to the plastic bottles that may arrive into our backyard, we could look for technological imprints on planets. For example, there is a lot of discussion of funding new observatories, next generation observatories in astronomy that will search for oxygen in the atmospheres of planets around other stars. The problem with oxygen is that on Earth, there was primitive life, microbial life, very shortly after the Earth cooled. But for 2 billion years, roughly half the lifetime of the Earth, there was not much oxygen in the Earth's atmosphere. We know that the oxygen level rose quite sharply after 2 billion years. So if you don't find oxygen, it doesn't tell you whether life does not exist. It may be that it's the early phase of the Earth, half of its life, it's a substantial fraction. So you could find planets with no oxygen that have life. And then if you do find oxygen, it doesn't tell you that there is life there, because you can make oxygen by natural processes, chemical processes. So it will never be conclusive. People will debate it. We will invest billions of dollars and we will not know. How can we know for sure that life exists? Well, if we use the same telescope, the same observatories to search for industrial pollution, the CFC molecules that we produce through our refrigerating systems, industries, and so forth, cannot be produced by nature. They are molecules that are very complex. And so if we find evidence for them using the same observatories, we would know that we have an industrial civilization on the planet that shows industrial pollution in its atmosphere. And actually, we wrote a paper about it in 2015 with a student of mine, and showed that the James Webb Space Telescope could potentially search for such industrial pollution at a level that is 100 times more than on Earth for planets in the habitable zone around white dwarfs, for example. But one can, in addition to industrial pollution, one can search for photovoltaic cells on the day side of a planet that use the light coming on the surface to convert it into electricity and then perhaps illuminate the night side. In a planet like Proxima b, the night side is permanent, so you want to bring artificial light to that side if you want to live there. And perhaps we can search for artificial light as well. We could search for swarms of satellites surrounding a planet as it transits the star. Or we can search for beams of radiation used for light propulsion of light sails, like the Starshot project. So when these beams sweep across our sky, they would appear as a flash of light, burst. And perhaps some of the bursts or flashes of light that we see relate to these technologies. So there are various ways for us to think about searching for technological signatures. And we just finished actually a textbook with Manasvi Lingam that should be published in 6 months or so, on June 25th of this year, 2021, by Harvard University Press. And will be more than 1,000 pages long, and I very much hope will lay the foundation for future research in the search for both biological signatures and technological signatures of life. Speaking about the light sails, maybe one should not only think about laser beams that are artificially produced, but in principle, you can harvest the light coming from a supernova explosion, the explosion of a very massive star. So in principle, you can park light sails at about 100 times the Earth-Sun separation away from a massive star that is about to explode, and then just wait. This approach is similar to what surfers do in Hawaii. They wait for a giant wave and then they surf on it. Here we are talking about surfing on a flash of light rather than an ocean wave. So if you park those light sails around a massive star that is about to explode, one can show that you can reach a fraction of the speed of light when the flash of light comes out of the explosion. And that's a nice way of enriching the Milky Way galaxy with light sails moving close to the speed of light without using any technology whatsoever. You just surf on the flash of light coming from a natural source. And the situation is similar to dandelion seeds that you can see on the right side here that are pushed by the wind. So Enrico Fermi, a very famous physicist who was involved in the Manhattan Project in Los Alamos, asked during lunchtime at some point with his research group at Los Alamos, he asked, well, indeed, it's quite likely that we are not alone, but if so, where is everybody? And this is called Fermi's paradox. Frankly, I find this paradox to be quite arrogant. It reminds me when I met my wife, she had friends that used to dream about Prince Charming on a white horse making them a marriage proposal one day. So they were waiting, but nothing came. Why would we think that we are sufficiently interesting for anyone to visit us or anyone to show their existence to us? The more natural assumption is that we are as common as ants on a sidewalk. And so when you walk down the street, you don't pay attention to every ant on the sidewalk. If there are so many life forms similar to us, why would we deserve special attention? We are not unusually developed. Another possible explanation to Fermi's paradox is that they are short-lived. Most of them are dead, because if you look at our civilization, we started developing our technologies 100 years ago, and maybe we will not survive for more than a few centuries into the future if we don't avoid changing the climate or having those self-inflicted wounds from our technologies. Then we might be short-lived. And if that's generic for technological civilization, that would explain, the short lifetime would explain why you don't get anyone on the other side when you're trying to make a phone call. On the other hand, if you're trying to look for a letter in the mail, you might find some, because these are relics left behind, longer lived than a radio message. There are other possibilities. For example, during the past year, I wrote a Scientific American article talking about social distancing on a cosmic scale. So you can imagine that when a civilization is sufficiently advanced, it establishes a habitat that is providing it with all its needs and just surrounds itself with a cocoon and is not interested in interacting with us, because we would only lower its quality of life. So they just socially distance from everyone else. That doesn't mean that we wouldn't know about their existence, because according to the second law of thermodynamics, they still need to deposit their trash. And just like investigative journalists that go to the trash cans of celebrities in Hollywood in order to find details about their private lives, we could infer the lifestyle of those civilizations by examining the trash that they deposit into space. So we can do space archaeology. We can look for artifacts of dead technological civilizations on other planets, look for megastructures, polluted atmospheres, relics like Oumuamua perhaps. And my hope is that by finding relics of civilizations that perished as a result of misbehaving, for example, as a result of changing their climate or having a war, that would inspire us to get our act together and avoid a similar fate. So we can learn a history lesson. And those civilizations that are still around, perhaps can offer us some technologies that would take us 1,000,000 years to develop ourselves. It might feel like cheating in an exam, just looking over the shoulder of the student next to you to find the solution. But if we save 1,000,000 years in this process, it's worth it. And in February 18 this year, just in a couple of weeks, the Perseverance rover will land on the surface of Mars and search for microbial life, signatures of life, either in the past history of Mars or at present. And that would be very exciting. I very much look forward to see what they find. So the search continues. Of course, this would be primitive life. What I really care about is intelligent life. And I hope you will enjoy reading my book where I discuss more details about that. Thank you.
Thank you so much, Avi. This was wonderful. And I know we have several questions for you, so I'm going to try to get control back here from Zoom. It does not want me to do what I want to do. All right, here we go. All right, so we have a few questions out there. And so what I'm going to ask is for Stephen to come back and read out some of the questions. Stephen, let's start with the chat in Zoom, and then we'll move on to the chat in YouTube.
Okay. Okay, the first question from Frank is, we think Oumuamua was tumbling based on its light curve. Would an interstellar light sail likely move in such a manner, assuming it was launched precisely oriented toward its origin?
No, so that leads me to the natural inference that it's probably not functional anymore. That, and it doesn't need to be necessarily a light sail. It could be a surface layer that was torn apart from a spaceship or something else. The point is that it needs to be very thin. If you remember, this rocket booster that we launched in 1966 also shows a push away from the sun. So it just needs to be a thin object. And I'm not sure what its purpose is and whether it's functional or not. Most likely not, because after billions of years in space, most objects in space would be billions of years old, because that's the longest time over which things were deposited in space. The chance of seeing something young is relatively small. So I would assume that it's most likely space trash. But there is one hint that comes from it residing in the local standard of rest. So why is it there? That's peculiar. And one possibility that I could think of, if it's one member of a population of objects that sort of populate a grid in the local standard of rest, so that when you navigate through that space with a spacecraft, you know where you are. You can find your coordinates. Another possibility is that it's a set of relay stations used for communication. So you don't need to transmit a very powerful beacon. You can just relay the signal across interstellar space. But all of these are speculations about the purpose of this object or other objects of the same. I should say the fact that we detected it over a few years implies that if we continue for a few years, we will find another one. There is no reason to think that we did it at a privileged time. That's called the Copernican principle, that we are not at a privileged place, nor at a privileged time. So we should find more of the same. It's just like the experience when you go into the kitchen, and you see one ant on your cabinet, you know that there must be many more ants out there. So we should just search for more of the same, and then of course get as much data, as much information about those that look weird as Oumuamua.
Okay, another question on it seems non-ideal for exploratory object to have spin and to have been launched at local rest speed or lack of. Were there any indications that it was attempting to communicate back to someplace or with us?
Right. So the tumbling, is most likely due to kicks that it got along its path, and the fact that it's tumbling means that it's not in control of its orientation. So this is just a natural consequence of an object not being functional. But with respect to communication, so about a week after the object was discovered, I met with Yuri Milner at his home in Palo Alto, and we discussed using radio telescopes that he had access to through Breakthrough Listen. That's another initiative that the Breakthrough Foundation funds, to just check if there is any radio transmission from this object. And we checked, and we put an upper limit of the power of a cell phone. So there cannot be even a cell phone transmission at gigahertz frequencies coming from Oumuamua. But of course, that was limited to anything sent in our direction during the time of the observation. So it's possible that, first of all, it doesn't transmit at gigahertz frequencies. Second, that it transmits sporadically because it saves energy, and we didn't look at the right time. Third, that it transmits in a direction that is completely different than the Earth's direction. But the most natural thing is to assume that it's not really transmitting anything. And, it's not functional. I mean, I would assume that it's not functional because most objects after billions of years are probably not useful for anything, just like plastic bottles on the beach.
Okay, thank you. One other question. Stephen Hawking thinks there are 13 dimensions. What do you say?
Oh, no, I mean, my point about extra dimensions or string theory or multiverse is not so much that the idea, is ruled out by anything, but the fact that we don't have any experimental tests of those notions, and yet they occupy center stage in the mainstream. And I find that to be frustrating because it demonstrates to me that physics is viewed by the majority of the practitioners as a sandbox for demonstrating that you are smart. And so if you don't put any skin in the game, if you don't make predictions that can be tested by experiments, then you are very safe from making mistakes, because unlike Einstein that said maybe black holes don't exist, gravitational waves don't exist, and that was proven wrong, you're not making any predictions about what you might find in reality, and therefore you're safe. So you can get awards, honors, and at the same time you do mathematical gymnastics and demonstrate that you're smart. That's a very comfortable spot to be in for a mathematician, but not for a physicist. I would argue that it goes against the premise of physics. Physics is a learning experience. We are supposed to have a dialogue with nature. not a monologue. We're supposed to listen to what experiments tell us and educate us. And sometimes they don't quite line up with what we expected. And that's actually the most thrilling experience that a physicist can have, because it teaches us something new. So when a seminar took place at Harvard about Oumuamua, I remember leaving the room along with a colleague of mine that worked on rocks in the solar system for decades. And my colleague said, "This object is so weird, I wish it never existed." I was appalled by this statement, because it's exactly the opposite statement to the one that he should have made. I find it actually exciting when something new comes along, when there is an anomaly, something doesn't line up with our preconceptions, because this is nature's way of telling us that we have to revise our preconception, that we were not assuming the right thing. However, if you insist that all objects in the sky are rocks and it's never aliens, then you act just like a caveman that is used to playing with rocks all of his life, and then when presented with a cell phone would say the cell phone is just a shiny rock. We don't want to be in that position. I just find it really strange, because the public is excited about this question. The public funds science, and then the scientists put a taboo on such interpretations. How is that possible? How is that acceptable?
Okay, thank you, Doctor. Another question. Are there any pending projects to demonstrate the practical use of light sails?
Yes. The Planetary Society is, of course, interested in using sunlight for that purpose. There was already a demonstration by the Japanese space agency, JAXA, and the Starshot project is working on a similar technology, except using a laser to propel the sail. There is some preliminary research done. I would not say that it got to the point where NASA would contemplate using it right now, but hopefully in the coming decades, it will become a technology that we use, because it offers the advantage that the spacecraft doesn't need to carry its fuel with it. So you can have a lightweight spacecraft and boost it to a relatively high speed. I should say that astronomers, when they search for rocks, they look for objects that move at tens of kilometers per second. But if there are smaller objects that move at very high speeds, like the breakthrough Starshot probes, they would not be noticed by astronomers. They move too fast. They are too small in terms of the amount of sunlight that is reflected. There might be a lot of objects passing through the solar system that we don't know about.
Okay, one last one I see here. Would you go as far to say any purely mathematical theories are just philosophy and not real physics?
I would say that they are closer to being mathematics than being physics, because the key signature of doing physics is putting skin in the game. Basically making predictions that can be tested and potentially be proven wrong. I was on a panel with Alan Guth, who pioneered the theory of cosmic inflation. And I asked a simple question. I said, is cosmic inflation falsifiable? Can you imagine any data set in cosmology that would rule it out? So in other words, if we find X and not Y, the theory will be proven wrong. That's a simple question. And he said, this is a silly question. Inflation cannot be proven wrong. So irrespective of what you find, it will be right. A similar situation happened at a colloquium at the Black Hole Initiative, where a string theorist was saying, in fact, in the landscape of string theory, you would expect some forms of the early universe or inflation to behave one way. And I said, great. So now suppose we observe the microwave background and we find that the early universe did not behave that way. Would that rule out string theory? And the speaker said, no, it will just rule out the connection that I made between string theory and the early universe. String theory will always be right. Now, I find this culture of physicists that not putting any skin in the game, but also denying the need to have experimental verification as quite dangerous to the scientific endeavor, because it's sort of like being high on drugs, like thinking that reality is whatever makes you happy. The thing is, you can be happy imagining that you are wealthier than Elon Musk, right? That's a happy thought. You can be happy imagining that you are at the center of the universe. That's also a happy thought. It flatters your ego. That's what Aristotle contemplated, and a lot of people prefer to believe him, including the philosophers during the days of Galileo that didn't want to look through Galileo's telescope. So you can have happy ideas, but if you want to cash these ideas and make them a reality, like if you want to use the money that you think you have and you go to the bank, you will find out that you don't have that money. So going to the bank is equivalent to doing an experiment. A lot of our most beautiful ideas, Aristotle's view of spheres surrounding us at the center of the universe was a beautiful, mathematically sophisticated idea. It was not, obviously it demonstrated that Aristotle is smart, but it was wrong. Reality doesn't need to be complicated, doesn't need to be described by fancy math that demonstrate that we are smart. It can be simple. It can be summarized by a few sentences, and that's it. Now, if we want to understand reality, we have to realize that it's not about us. It's about trying to figure out what reality is, and that's the goal of physics. And so I see a distortion of the objective of physics among the mainstream of the physics community, of the theoretical physics community. And I find it to be dangerous because if you propose a theory that can never be proven wrong, it's not really physics. We don't learn anything new because it's all, it's not as if you can revise your notions to make them right. And nobody would have thought about quantum mechanics out of the blue. It came about because of experiments. And then Einstein resisted the interpretation of those experiments that didn't look intuitive to him, but he was wrong. So we should let nature educate us rather than close ourselves in a door and make a monologue about what nature is supposed to be just because it's a sandbox that illustrates how smart we are relative to each other. So on the one hand, you have this culture. On the other hand, you have those arguments that searching for technological signatures is speculative. Talking about them is speculative. We shouldn't engage in that. And how is that possible? We know that we exist. We know that conditions on Earth are replicated in so many other planets. That should be mainstream. Everyone should assume that we are not unique or special and that we should search for things like that. And instead, it's being pushed to the sideways. So I find the situation unhealthy right now in the academic community. It's exactly in the opposite place of where it's supposed to be. It's not a small nuance. There needs to be a cultural shift. And my book, in part, is trying to explain the rationale behind such a cultural shift.
Oh, okay, thank you. And one last question. Do you have any comments on the implications for cosmology on the detection of gravity waves using pulsar timing arrays versus LIGO?
Yeah, so we actually wrote a paper with a postdoc, Dan Dorazio, that showed that detecting gravitational waves with pulsar timing arrays offers a very interesting way of inferring redshift without an electromagnetic counterpart. And the idea is, if you imagine a source at some distance, source of gravitational waves, so no electromagnetic wave emitted together with it, just gravitational wave, let's say two black holes that are bare, no matter around them, they emit gravitational waves. The wavefront of the waves is curved, right? It's a spherical wavefront propagating in our direction. And there is some curvature to this wavefront. If the source was at infinity, the wavefront will be planar. But since the source is at a finite distance, there is some curvature. And then if you imagine a pulsar detecting this wavefront and us detecting this wavefront, there would be some delay because of the curvature of the wavefront relative to the two detectors. And it's the same idea as parallax. So parallax traditionally is that the Earth moves around the sun, and we can detect how far the source is based on the change in the position of the Earth as it moves around the sun. But you can apply the same idea to gravitational waves, and you can use pulsars to infer the curvature of the wavefront such that you can measure both the redshift and the distance of the source. And that is interesting because without an electromagnetic counterpart, you could constrain cosmological parameters. But you probably meant something else. You were asking perhaps the use of pulsar timing arrays to measure coalescence of supermassive black holes that otherwise we have no way of inferring their existence until LISA is launched. And of course, the one problem right now is that Arecibo collapsed, and Arecibo was important for the pulsar timing array data, but there was already a hint for a detection with pulsar timing arrays, and I think they probe a very important part of the frequency regime that other detectors will not access. So, for example, one important question that can be answered with pulsar timing arrays is, how many mergers we have over cosmic history of supermassive black holes, and that is influenced not just by the emission of gravitational waves that brings tight black hole binaries together, but it's also influenced by the existence of accretion disks around those black holes because they help them come together even faster. So if there is a lot of gas around black hole binaries, it will make them short-lived. It will bring them together faster, and then you won't see anything with pulsar timing arrays. So we could constrain not just the population of black holes, supermassive black holes, which we know about from other measurements, but we can constrain the abundance of accretion disks of gas around them. And altogether, I think it's a very useful probe of the history of black holes throughout the age of the universe. And ultimately, LISA will be launched in about a decade. So it will probe similar black holes as well. And combining LISA with LIGO and Virgo and other gravitational wave detectors, will give us a broad view on black holes in the universe that we never had before. So I find gravitational wave astrophysics to be an extremely exciting frontier. And one thing that I could tell the younger people in the audience is this field was ridiculed a decade ago. I remember giving a lecture in a winter school, Jerusalem winter school, about 9 years ago on gravitational wave astrophysics. And another lecturer in that winter school, 10 minutes into my talk, raised his hand and said, why are you wasting the time of these graduate students on a subject that will never be important during their careers? And he said that just a couple of years before LIGO detected the first signal. And these students were still completing their PhDs when LIGO detected the first signal. So this illustrates to you how mainstream tenured professors can be hostile to new frontiers and be short-sighted in a matter of just a few years from the first discovery of a signal in those contexts. And I think it's a very important lesson to keep in mind when new frontiers are being proposed and explored. Just don't listen to experts. Thank you.
Okay, that wraps it up. We have a lot of thank yous, and I thank you myself, Avi, and we'll turn it back over to Amy.
Great. Thank you so much, Stephen. And Dr. Loeb, thank you so much for being here with us today and for sharing your thoughts. And I agree with you, when we look at all of the different frontiers that are being explored now through radio astronomy, heliophysics, doing things that we never thought we were able to do. And so it's amazing to hear what you are learning and what you are working on. And I'm very lucky because I get to hear from you all the time. It's a daily thing for me that I get to have that opportunity to speak with you, but being able to have you reach out further into the community, very deep into Arizona. We have a lot of Arizonans here today out by the Whipple Observatory, as well as to our worldwide community, has been just amazing to be able to work with you in this way. And since I don't see you a lot anyway, the separation of 2,000 miles. So it's nice to see you. And everyone, thank you so much for coming out today. The video will continue to be available on YouTube. So you can always go to our YouTube channel and check it out there. And don't forget that our next lecture coming up is with Dr. Simon Radford from the Submillimeter Array in Hawaii. So if you didn't know, we have people in 9 different science divisions thinking about all sorts of different topics in astrophysics and from different corners of the world. So thank you again so much, and we'll see you again soon.